Yeah, you are correct.
Loaded liposomes for bedside.
Okay, thank you so much, Meir. And I thank you for inviting me and Karen, which will probably come in a few minutes, to talk about a few aspects regarding liposomes. Actually, this part was the last part of the presentation, and Karen should have gave you the scientific part, and I'm presenting here the industrial aspects of liposomal formulation and production. Okay, but we switched, and I hope it's fine with you. I'm coming from Lipocure. It's a startup company located in Jerusalem. Our co-founder of the company is Chezi Baranholtz, which gave his talk on the first day of the conference. And I am one of the scientists in the company, and I am the project manager of the methylprednisolone, which is a steroid, which is encapsulated into a nanoliposome. A few words about the company. We are located in the Hadassah Medical School campus. As you can see here, this is Chezi, this is me. Wolf, which is sitting on the lower side of the line here, joined Danny's lab, I think it was a year ago, so this is an old picture. And what we do, actually, we are an R&D company, R&D related to nanomedicines and liposomes. We have a pipeline which includes doxorubicin-loaded liposomes in a new formulation which named LC100. LC200 is the project that I manage, which is steroids inside liposomes. The indications are optic neuritis, multiple sclerosis, rheumatic arthritis, and lupus. Karen will describe two indications of this LC200 project after me. The third pipeline product is LC300, which is a combination of topotecan and vincristine liposomal formulation. And the fourth is a structure of hydrogel with liposomes with bupivacaine inside for post-operative pain. As you could hear about the names of the drugs, if it rings a bell, all of them are already in clinical use. As a startup company, we don't have the funds to use new molecules, and we use a well-known, especially from the toxicity aspect, molecules, and we have our technology to encapsulate these molecules into the liposomes. This is, if someone wants additional information, this is the 505(b)(2) FDA approval line of approval of agents or clinical applications related to these well-known agents. So probably after these few days, you probably know something about nanocarriers, nanoparticles. I hope that you learned something. I will describe most of the work here, all of the work here regarding the particle, which is the liposomes. Okay, it's a bilayer. I will not get into details. No science in my lecture, not so much. And what I want, my outcome from this lecture, I hope that you will enjoy it, of course, but the outcome from my lecture actually brings you to the industry. And as a scientist in the academia, I thought that it would be nice to show you the next step of your 1 ml formulation on the bench. Think about us, because when you develop something that is very complicated, when I will try to formulate it in an upscaled volume, it will be very, very, very complicated to manufacture. And also the regulator, the FDA or the European regulator, will ask a lot of questions. So make it simple as you can. And of course, we are open to very sophisticated technologies, but start with the simple ideas. So liposomes. As you probably heard before, there is, I will speak here about, I gave examples about the doxorubicin-loaded liposomes. The Myosat was developed 15, 20 years ago. It is a non-pegylated liposome. It is not FDA approved. It is only used in the European area, in Europe and in Canada, if I'm not wrong. And the reason it's not really used and wasn't approved by the FDA is because since it is not pegylated, polyethylene glycol agents or polyethylene glycols on the surface of the liposomes, as you can see on the right side of the structures, the macrophages just make it short circulated in the circulation, which means that you will have less effect. The PK or the release of the drug profile will be a little bit different or not sufficient for cancer. That's the reason this agent is approved only for cancer in combination. For that purposes, 20 years ago, Peter Kurz, which is here, and additional scientists from all around the world, thought about adding polyethylene glycol to the surfaces of the liposomes, the nanocarriers. It is a well-known effect which will enable us a long circulating time for the carrier. Doxil and Calyx are the original drugs that are on the market. Doxil is not, Calyx is not. There was a shortage a few years ago. Lipodox, which is an Indian company, now manufacturing the generic version. And Doxil is, I think that they might start again to produce it in the next year. So, as for the second option, the B, this is the pegylated liposomes. There are additional liposomal formulation in the market. I decided to focus only on the doxorubicin-loaded ones. Let's move to the sophisticated one on the right side of the slide. Can it be done? I think so, yeah. Did you see any liposomal drug which is connected to an active targeted agent like an antibody or peptide? Probably yes in your labs, maybe in a phase 1, 2, maybe in phase 3. But none of them got into the clinic so far. What can be done is this slide. We can add antibodies, ligands. We can add peptides on the surface on the carrier, which will enable us to penetrate the cell and get our liposome with the drug or with the siRNA, for example, to specific organelles inside the cell, nucleus, membrane, for example. We can have a multifunctional liposomal carrier. We can add a peptide and an antibody and additional imaging agents. On the surface of the carrier, we can add a few drugs inside. This is a very nice idea. People are publishing and keep publishing these liposomal formulations, but think about industry. Okay? It is very complicated to formulate this kind of nice formulation in the industry. So, in brief, I will start exploring your thoughts. I will start to explain how do we formulate liposomes in a small scale, and then we will move to the large scale. So liposomes in general, it's lipids in an aqueous solution. We can have the lipids in a flask, and then we can add our aqueous phase with the drug, without a drug, depends if you want to load the drug actively or passively. After mixing, we will get a liposomal formulation or liposomal structure which named multilamellar vesicle. This is a structure. We will downsize the particle because this multilamellar vesicle is 1 micron, and after downsizing the particle, we will get up to 50 to 100 nanometers. So we are moving from multilamellar vesicles, which is between 1 micron to 500 nanometers, to 20 to 100 nanometers. Okay, and we are in the lab trying to formulate 1 ml of liposomes. Did anyone here try to formulate liposomes? Good. I hope after the lecture you can go to your labs and start making it in liters, I hope. Okay, so first when we try to design our production process, we need to know what are our risk assessments. What will not work really good? What are the trends of the process that might not work as it worked on my bench? Okay, it is very important because every batch might cost $100,000, and you don't want to waste it because the temperature wasn't high enough or low enough, or additional parameters that influence your final product. Production of liposomes is a very complicated thing physically, and also physico-chemically, I mean, and also it needs to be done in aseptic conditions. This is me, by the way. Once we upscaled all our line of production, I had to go inside the clean rooms and try to make it by myself to see how it works. Okay? Working with huge tanks is different than working with small tubes. Okay? So aseptic conditions means that all the process, from the mixing of the lipids to the filling in the bottles, everything should be aseptic, meaning sterile. Okay? This is in general sterile. It is very hard to do it. Everything that you get into this room is sterile. Okay? And imagine that you have 200 liters of a solution. All the agents, all the materials, everything is sterile. So it's a very, very difficult way of doing it. I tried to make a production process figure that you will understand, and we will just move from one stage to the other stage. And I designed the lecture like that we will move from the first initial stage until you will see the bottle with the drug. MLV production is the first stage. We have big tanks, and we prefer the glassware because we can see what's happening inside once we mix the liquids with the lipids, the aqueous solution, aqueous with the lipids. Different ways of looking. This is the lab picture of lipids that were added into the aqueous solution. You can see from the right that it looks different than from the left. The only difference between these pictures are once we had A solution that was added into B, and the second one is B into A. We have a lot of parameters: speed of steering, temperature, pressure. Each parameter counts. Okay? And remember, we don't have second chance, at least unless you have an unlimited funds to try. Multilamellar vesicles look like that. You can see it's like an onion. Let's take this liposome as an example. This is the first step. Okay? Once we mix the lipids with the aqueous solution, we will have this multilamellar vesicle. When we load the drug with our systems, the aqueous solution includes a salt, ammonium sulfate for doxorubicin, for example, or calcium acetate for methylprednisolone, which will be my next talk, the next talk by Koren, the half of the talk, the next half. So following our MLV production, we check the size. We can see that we get something like, let's see here, 1 micron. In general, it's okay for MLVs. Second step is extrusion. We want to downsize the particles. Okay, so we start with a 1 micron particle. The end point should be 80 to 100, depends on our specification for the specific product. So we use filters. The filters are polycarbonate filters. They have tiny nano holes, which are, the range of the holes is between 50 nanometers to 400. And that's the way we downsize the lipids or the MLVs, the multilamellar vesicles, from big liposomes into a single unilamellar vesicle. Scanning electron microscopy of the filters is this figure. And you can see that from 400, the size of the holes gets smaller, and followed by this decrease in the holes range and size. You can see that from MLV, we get into small unilamellar vesicle. Okay, this is an extruder, 1 ml extruder. This is how we formulate liposomes on the bench. Imagine this kind of machine for 100 liters. Can you imagine a huge syringe, or in someone that is pushing it from one side to the other side? The basics of this extruder is 2 syringes from 2 sides, and in the middle you have this filter. Once you moved your solution from one side to the other, it went through the filter. The size is decreased, of course. And you can change the filters along the process, of course. So this is for lab scale, of course. We have a medium scale extruder for 10 mLs. This will include nitrogen pressure from here. Liposomes will be inside this chamber. We can heat with a heat jacket. The filter is here, and the liposomes go from up until they go out through the tube in the bottom of this extruder. But still, this is a 10 ml extruder. So there is a family of extruders. From the right, from 10 mLs to 1 liter, if I'm not wrong. This is the right one. But we are speaking about 100 liters of production, right? So there is no available extruder in this kind of volumes. And there are not more than 5 companies in the world that knows how to formulate liposomes in these volumes. We are one of them. So we have our engineers, and following the experience during the years, we build our costume-made extruder. Okay, the basics are the same, but it is costume-made to our needs, of course. There is a machine that's named Homogenizer. It is mostly used in the food industry, but we can use it also for downsizing liposomes. We already did it. It works. But as now, we are still working with the traditional way of formulating liposomes, which is the filters, the pressure, the temperature. In the future, I'm sure that these systems will be used for a mass production of liposomes. And just to give you an example of how it looks like, when we started with 1 micron of MLVs, big liposomes, we continue cycle after cycle with changing the filters. We get 140, 107, 91, and the final product is 80 nanometers. Which is our main goal, or the specification. It stands in our specifications for the product. This is a picture which is a nice view of empty liposomes. Okay, in a few minutes they will not be empty, so you can wait. Dye filtration. Once we have the liposomes, we want to have a gradient. Okay, as Professor Chezi Barnolds probably told you in the first day, we are using a gradient to suck the drug inside the liposomes. So we need to have high concentration of salt inside the liposome and extra liposomal solution with very low concentration of this salt. This is a gradient, of course. And for that purposes, we can use VivaSpin systems in the lab. This is for 1 ml. We can have dialysis bags. If it is larger volumes, but still, this is a lab scale. The dye filtration concept allows us to use a small system that will dye filtrate large amounts of liquids. And we have these tiny holes that the solution can get out, but the liposomes are staying in a circulating way inside the system. It looks like that when we are speaking about a lab-scale system of diafiltration. The liposomes are circulating inside the system, while from here they just go out. But the liposomes are not getting out. Only the solution, the extra liposomal volume, is getting out. A new solution of sucrose, for example, gets in, meaning that 1 ml gets out, 1 ml goes in, and then we will have a balance of the volume, decrease in the extra liposomal concentration of the salt, and a gradient formation. In the real life, when we come to formulate hundreds of liters, we need to have huge system. The basics of this system is the basics of the system that I showed you before. There are hollow fibers inside these tubes, and once it is in parallel, you can accelerate your process of diafiltration for mass production, for example. Next step is drug loading. After I have a liposomes with a gradient, high concentration of the salt inside, low concentration of the salt outside the liposomes. A drug that will prefer to be inside the liposomes will just sucked in by this chemical pump. So we are just mixing the liposomes with the drug to get an encapsulated drug inside the liposome. It's not so simple. It looks simple. We have to control all the parameters of temperature, pressure, and mixing rates, and it doesn't work all the time unless you know what you are doing. So the process, even if it's mixing two agents to get the third one, is controlled in a very, very strict way in order to repeat it again and again. After I added the drug, you can see the doxorubicin in this case inside the liposomes. In the other case of steroids, you will not see these crystals inside, and you will probably see it as the dots. Koren will show it in a minute. And we can control the shape of the liposomes. In addition to the size, post-loading of the drug, we have the ability to control the shape. Okay, so I can offer someone who does a research, for example, about the influence of shape on the efficacy, on the PK, this kind of technology. Okay? You can see that if we loaded the drug in a very high amount of loading efficiencies, the liposome will just rupture and the drug will get out. So this step should be controlled in a very sensitive way. Okay, I'm getting into it. Final filtration. This step only took us around 4 months to develop. Okay? It looks very easy. Okay, we have in the labs these filters. It's very nice, 0.22 microns. Okay, let's buy a new one, a bigger one. Try to move this huge tank through this filter, and that's it. 4 months. Okay? So it's not so easy. And I know from my sources that other companies are having problems with this kind of stage or this filtration process. Okay? So it's not so easy to filtrate our liposomes in this case, but I think it works in additional platforms. Once we have succeeded to filtrate our liposomes, next step is the filling, of course, into the bottles. And this was the first bottle that was filled in our process. So it's not me. Don't worry about it. I'm the photographer. And from this stage, I can tell you that after this long way of the development of production of liposomes, I just want to ask you guys, as the scientists, try to be simple. Okay? This is what I think should be the main outcome from my lecture. Thank you so much. And my time, I think, is limited because Koren has additional short lecture, so I will answer one question.